All right, this is the last lecture for Chapter 9. We are on page 35 of the student note packet. We're going to do 4 examples, and then you guys, part of your homework assignment is to do the examples on page 36. So don't forget those numbers 1 and 2, and then the bookwork there. All right, so review really quickly of the last lecture. Complex numbers in rectangular form look like the top equation. There's z is equal to a plus bi. There's that real component that's represented by a, and then the imaginary component represented by b. We just did a lecture on then converting complex numbers in rectangular form to polar form. And then the polar form looks like that. Z is equal to r times the quantity cosine theta plus I sine theta. And we can convert between the two, and then we can multiply complex numbers in polar form. We learned how to divide complex numbers in polar form or raise a complex number in polar form to a power. So we're going to kind of build on that last piece, especially today, the powers of a complex number in polar form, but we're going to be taking roots instead. So it's very similar to how we raise a complex number in polar form to a power, except for when we take the root of something, the power then becomes fractional. So we're kind of thinking back to like chapter 5, which was last semester, and the rules of exponents and logs. If we take the root of something, it's like raising it to the fractional power. So that's kind of what we're going to apply. And so the equation for roots looks really, really similar to the equation to raise a complex number in polar form to a power. We're just dividing theta by that root instead of multiplying it. Right? Okay, so let's do a couple of examples, and then you guys can get started on your homework. So find the cube roots of this polar complex number, 8 cosine 60 plus I sine 60. We do have an equation. All right, and that equation tells us that the cube root of z is what we're trying to do, is the same thing as taking z, raising it to the power of 1/3. And we do that by taking the value of r, raising it to that power. And then on the inside, we take our angle, we divide it by 3, right? Or essentially, we're multiplying it by that fraction, times 1/3. Okay, we're going to do that for sine as well. So what happens is when I simplify, 8 to the power of 1/3, or the cube root of 8 is 2. And then I get the cosine of 20 plus I times the sine of 20. All right, so there's one of our roots. Now, here's the deal. There is this thing called the fundamental theorem of algebra. Might be ringing a bell from algebra 2, or the linear factorization theorem, but that tells us that a polynomial of some degree n has exactly n linear factors. So what that means is when we're taking the cube root of this complex number, we actually should have 3 answers or 3 solutions here. So more than just 2 times the cosine of 20 plus I times the sine of 20 cubed is going to get us back to our original complex number. We could also say, right, think about all of the other angles that are coterminal with 60. So 60 plus 360 is 420. So I could have said, instead of 60 divided by 3, 420 divided by 3. Right? Well, that gets us 2 times the cosine of 140 plus I times the sine of 140. And that's a distinct root. It is not the same as our first solution, which was the cosine of 20. Right? Now think of another angle that is coterminal with 60. Well, 60 plus 360 plus another 360 is 780. So instead of saying 60 divided by 3, we could have said 780 divided by 3. It's the same angle on the unit circle, just expressed differently. And when we clean that up, when we simplify that, that is 2 times the cosine of 260. And that's another distinct root. It's not the same as any of the other 2 that we've got. Right? So then we find another angle that's coterminal with 60, 420, 780. Add another 360 to 780. 1140 is also coterminal with all of those angles. When I simplify this, 1140 divided by 3. Okay, that is 380. Now, 380 degrees is coterminal with one of our other solutions, right? But that's coterminal with 20 degrees. So that is not a distinct solution. We don't include that in our solution set. But there are 3 roots here. So we're going to look for patterns so we don't have to keep trying to figure out all of these coterminal angles with our original angle. When we're looking for the cube roots of a complex number, we're going to have 3 solutions. If we're looking for the 4th roots of a complex number, we'll have 4 solutions. If we're looking for the 6th roots, we'll have 6 solutions. So we can easily determine the number of solutions. We just need to figure out how to get there. So let's compare the angles that we had. 20, 140, 260. They're evenly spaced, right? What do I do to get from 20 to 140? Well, I add 120. Same thing here. I add 120. So if we can figure out how to find that spacing, then we can figure out how to kind of shortcut the way to find the roots of a complex number. So 120, all that does is it just comes from 360 divided by the number of roots we're taking, right? Which in this case is 3. So we can find the spacing by just taking 360 divided by the number of roots we're looking for. Now, the last thing you guys are going to do on your homework is you're going to draw or include the Argand diagram, because this is something I'm going to ask you guys to do on the test. So essentially, you're just going to sketch out each of these roots. All right, so the first one is at 20 degrees, maybe right there. The second one is at 140 degrees, something like that. Right, we want the length of these to be the same too. And then 260, that's like really, really close to 270 there. There you go. That's what the Argand diagram looks like. It's just a sketch of all of the roots. All right, so we're going to do that for B, C, and D, and then you guys are going to do the same thing for your homework. We're going to use the shortcut so I don't have to think about all the angles that are coterminal with the angle we're starting with. And we'll take a look at example B now. So we want to find the 4th roots of this complex number in polar form. Now, 4th roots means we're going to have 4 solutions, right? And the spacing is going to be 360. Let me write that down, just spacing. Divided by the number of solutions here. So every root is going to be 90 degrees greater than the last. All right, so we are taking the 4th root of our complex number. It's the same thing as taking our complex number, raising it to the power of 1/4. So 625 to the power of 1/4 times the cosine of 300 divided by 4 plus I times the sine of 300 divided by 4. All right, and we simplify. So 625 is 5 to the 4th power. So the 4th root of 625 is 5. And then 300 divided by 4 is 75. All right, so there's solution 1. Next solution, we know we're going to have 4, is just 75 plus 90. So our spacing, remember, is 90 degrees. So 75 plus 90, that's going to get us to 165. And then the next one, another 90 degrees later, that's 255. And then our last solution here, 90 degrees later, 345. If we were going to add another 90, right, if we didn't stop at 4, we'd get to 435. And 435 is just coterminal with 75, so that wouldn't be a distinct root anyways. Last thing we do here is we just sketch the Argand diagram. So again, we're just going to go around and sketch each of these points. So 5 cosine 75 degrees, that's something like this, right? And we want to make sure that all of the legs are the same size because they have a distance of 5 from the pole. 165 degrees is over here. 255 down here. And then lastly, 345 over here. You should note that all of these are evenly spaced, as they should be, and they will be for every problem, right? And the length of each of these is 5. So don't forget to include those on your homework as well. I'll be looking for those diagrams. C is a little bit different though, and the problem with C is we don't have this complex number in polar form, and our equation to take a complex number and find the roots of it is only in polar. So what we have to do first is convert -64 in rectangular form to -64 in polar. To do that really quickly, where is -64? Well, that's the real component. That's the same thing as saying like plus 0i, right? So -64 puts us on the negative x-axis, 64 units from the origin. So we could also express this as 64 times the cosine of 180 plus I times the sine of 180. And now that we've got this number in polar form, we can then just find the cube root. So we're looking for cube roots here. That means there's going to be 3 distinct solutions, and the spacing of each of those solutions is 360 divided by 3. So the spacing here is going to be 120 degrees like it was in example A. So the cube root of our complex number z, same thing as raising it to the power of 1/3. Take 64, raise it to the 1/3 power, and then we're going to have 180 divided by 3 plus I times the sine of 180 divided by 3. Okay, the cube root of 64 is 4, and then this becomes the cosine of 60 plus I times the sine of 60. Now, it's the cube root here that we're finding. We know there's 3 solutions. The spacing is 360 divided by the number of solutions, so 360 divided by 3. Our angles are 120 degrees apart, so 60 plus 120 is 180. Then 180 plus 120, that's 300. Then if we were to continue adding 120, we would get to 420, and that's coterminal with 60, right? So that's not a distinct root. Sketch the Argand diagram for this, right? First angle is 60, and then 180, and then 300. So again, evenly spaced around the circle as they should be. Each of them has a length of 4 away from the pole, right? And technically they're points here, like that. Okay, pause the video, give D a try. Note that this is also not in polar form, so convert it to polar form first. Find the roots, sketch the diagram, and then when you're done, come back for the answer. Last one, solution here looks like that. There are 6 solutions because we're looking at the 6th root. So in addition, right, the spacing is 360 divided by 6. Each of these angles is 60 degrees apart from the last one. Diagram looks like that. That's it. All right, we are done with chapter 9's lectures. Make sure to do page 36 and then the book work. Email me if you have questions.